This section is just another way of finding volumes of solids of revolution. So in Unit 6.2, we would have a region, and let's just make a generic region here. And if I were revolving about the y-axis, I would make slices this way along the y-axis, so perpendicular to the axis of rotation. And I used washers or discs. So it was almost like I had a bunch of sheets of paper stacked on top of each other, and I was adding up the volume of each little sheet of paper. Well, this time instead, let's look at the same region that I just made up here. I'm going to make my slices parallel to the axis of rotation. So instead of having a bunch of little flat discs, I'm going to have a bunch of cylinders. So it's more like a big roll of paper towels, because we're looking at slices this way. So these are called shells. So when your slices are perpendicular to your axis of rotation, perpendicular, you get washers. If they're parallel, you get shells. It kind of rhymes to help you remember. So we have to think about the volume of these shells. Well, the volume of a cylinder is equal to pi r squared h. But now the textbook talks about finding the volume of each of these cylindrical shells, and you find the volume of the outer shell and subtract off the volume of an inner shell. So you have pi r squared h minus pi, the outside radius minus the inside radius. But when you do all of that and average them out, what helps me to remember it is you come up with the surface area, 2 pi r times the height, which is actually the surface area of one of those shells. So what you end up with is 2 pi times the radius of your shell, which in this case would be your x coordinate, times the height of your shell, which would be f of x. So your volume is going to be the integral from one end of your region to the other. So we'll say from A to B, 2 pi times the radius times the height, and then the thickness is always represented by your differential, and I'll say dx because in this particular example we're looking at slices along the x-axis. So let's do a real live example and put some real live numbers in here. And there's the pretty picture talking about the circumference, which is 2 pi times the radius times the height and the thickness. So we want to find the volume of the solid obtained by rotating about the y-axis, the region y equals 2x squared minus x cubed, and y equals 0. So I'm going to take a minute and make a set of axes for this. Now, you would be expected to be able to sketch this thing. So let's think back to pre-calculus in sketching polynomials, I have a odd degree, so I know the ends go in opposite directions, and the leading coefficient, which is the number sitting next to the biggest exponent, is negative. So I know it goes down in this direction and up in that direction. So as x approaches infinity, it's going down. I know that it touches the axis at x equals 0 because I went ahead and factored, and I have a 0 at 0 with multiplicity 2, so I know it's going to have to do this, and then it crosses the axis at 2, so 1, 2, so it's going to have to come up and then go down. Now, I don't know exactly what it looks like, but this is good enough for me to complete this problem. I know that my region is living here in quadrant 1 because it wants the area that's between this graph and y equals 0, which is the x-axis. So we're going to say that it's what is enclosed between those two. This is an infinite area. That would be an infinite area. So we're just looking at this little bubble right here. And we're going to rotate about the y-axis. Now, since we're rotating about the y-axis, if we're going to use shells, we need to make slices that are parallel to the y-axis, which means our slices are going to be along the x-axis. And we'll have something that looks like cylinders that look like that. So I'm going to write the equation again on the other side of my paper. So I just rewrote the function, and then I made myself a little graph so I can still keep my mind on what I'm doing. So I'm going to make a slice here on the x-axis, and this goes from 0 to 2, where it crossed the x-axis. So those are going to be my limits of integration because that's where I'm slicing. I'm going to draw in a cylinder. The radius of that cylinder is going to be x because I'm going about the y-axis. Your radius is always x when you're revolving around the y-axis. And then the height is going to be equal to whatever my function is, which is 2x squared minus x cubed. So my volume is going to be the integral from one end to the other, 0 to 2 pi times the radius times the height. dx represents the thickness of each of my cylinders. And now I'm not going to make you watch me do the integration. We have the circumference, or 2 pi times the radius. Here's the height, the thickness. You multiply through, add 1 to the exponent, divide by the new exponent, and you can verify that you get the exact same answer if you do it with slices. There's the pretty picture of the solid. So example 2, we want to find the volume of the solid obtained by rotating about the y-axis, the region between two functions. So y equals x and y equals x squared. We have drawn this quite a few times, so I'm just going to take a break and draw it. So I went ahead and drew my region, which lives right here, and then I just sketched in. I make my slice right here along the x-axis because that's parallel to the axis of rotation. My radius is equal to x, the distance to the axis of rotation of one of my cylinders here. And then the height is going to be the top function minus the bottom function. So my volume, I'm going from 0 to 1 because that's where they crossed. We figured that out last time by setting x equal to x squared. They cross at 0 and 1. 2 pi times the radius, or the circumference, times the height. And again, you don't need to watch me do algebra and simple integration. You end up with pi over 6. So, write this problem down, take a few minutes and see if you can do it on your own. We'll come back and compare answers. How'd it go? So first thing I did was get a little sketch of that parabola. I knew it was a sad parabola, and I knew that it crossed the axis at 0 and 4. Therefore, I knew that its vertex was between those 2 points, so I knew its vertex was at 2, so I plotted that point. You could always plug it into your calculator and it would tell you the vertex. And then I figured out where they crossed. They crossed at x equals 0 and x equals 3, and since this is the identity line, it's easy to know that it was the 0.33. And my radius, I went ahead and sketched in. Sorry about that. My radius is equal to the x value, and then my height is equal to the parabola minus the line. So 4x minus x squared is the parabola minus the line, y equals x, and I just combined like terms. And then I went ahead and did the integration. I simplified. I added 1 to the exponent divided by the new exponent, and I ended up with 27 pi over 2. Now, we want to use cylindrical shells. This time we're going around the x-axis to find the volume of the solid obtained by rotating y equals the square root of x from 0 to 1. So we don't have to figure out a intersection point because we're given our limits of integration. Example 3. So it always helps me to draw my own picture. I'm going to do y equals square root of x from 0 to 1. Shade in my region. Now, this time I am rotating about the x-axis. So I draw in my little arrow to remind myself which way I'm rotating. I want to use shells, so I'm going to have to make my slices parallel to this axis of rotation. So my slices are along the y-axis, which means I'm going to integrate with respect to y. WRT with respect to y. So my y's are going from 0 to 1. I need a function with y's in it. Well, y equals the square root of x. That means that x is equal to y squared. And now let's draw in a cylinder. This time the cylinder is surrounding that axis of rotation, which is the x-axis. So my radius is equal to y. The height of one of my cylinders is equal to 1 minus this function value, which is y squared. So my volume I'm going from 0 to 1, 2 pi times the radius, there's the circumference of my cylinder, times the height, which is 1 minus y squared dy. And there's the answer. You don't have to watch me do the algebra and the easy integration. Pi over 2. Your turn. So again, we're going around the x-axis. So we want to integrate with respect to y, which is kind of convenient since I have my function x equals y squared minus 4y plus 4. So sketch yourself a graph, practice sketching, and give this one a try. Okay, how'd it go? I went ahead and found where they intersected. So I said, actually, first I rewrote this as x is equal to 4 minus y to get it as a function of x with y's in it. Then I set them equal to one another, and I realized they crossed when y is equal to 0 and 3. I plugged y equals 0 in and got x equals 4, so I knew that it had to go through that point. I knew that this was a right opening parabola, so I figured out where it hit the axis, and it hits the axis when y is equal to 2. I got that by setting x equal to 0. And I see that y minus 2 squared equals 0, so I know that it touches there at y equals 2. So there's my parabola. And I get a region, looks something like that. I'm making slices that are parallel, actually, to the axis of rotation, which is the x-axis. So here's my representative slice and my representative cylinder. The radius is equal to the y-coordinate, and the height is the line minus the parabola. And then I simplified the line minus the parabola, and then it's funny, we ended up with the exact same answer as we did with this example, 27 pi over 2. Okay, example 4. Find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about a line that's not an axis. So just like with washers, we're not always going to revolve around an axis. We will only do perpendicular and horizontal axis of rotation. Vertical and horizontal axes of rotation. So let's look at example 4. We have y equals x minus x squared, and y equals 0. So that's the x-axis. And we want to go about the line y equals 2, x equals 2, and x equals 2 is a vertical line. So parallel to the y-axis, which means I want to integrate with respect to x. So first thing I need is a picture. The line x equals 2, 1, 2, pretty easy. That's my axis of rotation. Now, this parabola, y equals x minus x squared, I know it's a sad parabola. It opens downward. So x minus x squared is equal to 0. So x times 1 minus x is equal to 0. So x equals 0 and x equals 1. because 1 minus x equals 0. So it crosses right here at 0 and at 1, and it's sad. So it looks something like that. And I'm going to make it exaggerated, so not to scale, just so. There. Now, I'm making slices that are parallel to the axis of rotation. So it looks something like that. Here's my radius, goes from the axis of rotation to my cylinder. So my radius is going to be equal to 2 minus x. Bigger minus smaller, so 2 minus the x value. And the height is equal to this parabola, which is x minus x squared. So, integrating with respect to x, so I get my limits of integration along the x-axis from 0 to 1, 2 pi times the radius times the height dx, and there's the much prettier picture. And we had the radius, 2 minus x, times the height. We did some algebra, we did some calculus, and we get pi over 2. Most of these on test day I'm going to let you do with your calculator. You will be required to do a couple of them by hand. So find the volume generated by rotating the region bounded by 4 minus 2x, y equals 0, x equals 0, about x equals negative 1. So again, x equals negative 1 is a vertical line, so you know you're going to be integrating with respect to x. Take a minute, draw a picture, figure it out. You can do it. So this one kind of looks like a cone with the top cut off of it, but it's solid here at the corners. So my region was this triangle here enclosed by the line, and y equals 0, which is the x-axis, and x equals 0, which is the y-axis. We revolved it about the line x equals negative 1. So my radius is the distance from x equals negative 1 to one of my slices along the x-axis. And then the height is just the height of that line at that point. So radius x plus 1 or x minus negative 1. Height 4 minus 2x. And then it was easy. Okay, this one we're revolving about y equals negative 2. So that's going to be a horizontal line. We'll be making slices that are parallel to the axis of rotation. So we're going to need to integrate with respect to y, and luckily we have our functions with respect to y. So take a minute, give that one a try. We'll meet back and compare. Okay, we had two parabolas that opened up to the right. So I set them equal to one another first to see where they cross. And they crossed when y was equal to plus or minus 1. If I let y be equal to 0 in x equals 2y squared, I know it starts at the origin, and I know that it's skinny. And if I look at x equals y squared plus 1, when y is equal to 0, x is equal to 1, so its vertex is right here. So I knew that this one had to open up faster because it's not getting wide as fast, it's not growing as fast. So I found their intersection points when y is equal to plus or minus 1, when x is equal to 2. So I integrated from negative 1 to 1. My radius is equal to the distance from my y-coordinate to the axis of rotation, so y minus -2. My height is equal to the fat parabola minus the skinny parabola, so y squared plus 1 minus 2y squared, which is just 1 minus y squared. I did some foiling over here. I did some integrating and plugging and chugging, and neither of them was 0, so I had to plug both numbers in to get the answer. Okay, disk versus shells. Do whichever one is easy. Is the region more easily described by top and bottom or by right and left? If you're given functions with x's in them, maybe you want to integrate with respect to x, and that will define your choice. Does the region require two separate integrals one way and not the other? Are we able to evaluate the integral we set up with our choice of variable? It's just going to be easier one way than the other sometimes, and sometimes it doesn't matter. So let's look at example 5. We want the region in the first quadrant bounded by y equals x squared and y equals 2x. A solid is formed by rotating the region about the line x equals -1. We want to find the volume using x as a variable of integration. So, of course, I'm going to draw my own little picture. And we have y equals x squared, so everybody's favorite parabola. And we're only in the first quadrant, so I don't need the other side of it. And y equals 2x. So x squared equals 2x. X squared minus 2x equals 0. So x times x minus 2 equals 0. So x is 0 or x is 2, so 1, 2. So this is the point 2, 4. So there's my little quickie graph of that. Looks something like that. We're going around the line x equals -1. So no matter what y is, x is equal to -1, so it lives right over here. So this is my axis of rotation. If I make slices along the x-axis, are parallel to axis of rotation. Which implies shells. So let's do the shells first because I like x as my variable of integration, and that's what number 1 is anyway. So that means I need a radius, and let's make a little shell here. The radius of my shell, and that's not a very accurate shell, but that's okay. I can see the radius is from my shell to the axis of rotation, so it's going to be x minus -1, which is x plus 1. My height is going to be the line minus the parabola, so 2x minus x squared. So the volume would be the integral as x goes from 0 to 2 of 2 pi times x plus 1 times 2x minus x squared dx. And that takes a little algebra. There's my pretty solution. I multiplied it out, and I got 16 pi over 3. Now I'm going to draw myself another quick graph of this thing. So here's my parabola. Here's my line. This is the point 24. Here's my axis of rotation. This is my region again. This time I'm making slices along the y-axis. So I'm going to have an outer radius and an inner radius. My slices are going to vary from the bottom to the top. Now, my functions are y equals x squared, which means that x is the square root of y, because I'm on the right side of the y-axis, and y equals 2x, which means x is equal to y over 2. So my volume, actually let's write down my radii first. My outer radius is the distance from the parabola to -1, and so it would be square root of y minus -1, which is square root of y plus 1. My inner radius would be equal to y over 2 minus -1. So y over 2 plus 1. So my volume, my integral is going to go from 0 to 4, because that's where my slices go, pi times the outside radius squared, so square root of y plus 1 squared, minus the inside radius squared. Outside radius squared, inside radius squared, and looks like I have a typo there. Yeah, because I have the 1/2 down here where I squared it. So I'll go in there and fix it. You'll never know. But I end up with 16 pi over 3. Let's look at practice problem number 5. We have y equals x squared, not cubed. I had a typo there earlier, and I wrote down my typo. It should be x squared, and y equals 8 times the square root of x about the y-axis. And we want to do it both ways, with respect to x and with respect to y, which means we're going to use shells, and we're going to use discs or washers. So let's sketch ourselves a little graph of this. So first let's set them equal to each other. X squared equals 8 times the square root of x. Well, I know it's got to be in the first quadrant because x squared looks like this, and square root of x looks like that, and multiplying it by 8, it's still going to look kind of the same. We just have to figure out exactly where this point is where they cross. So I square both sides. That gives me x to the 4th equals 8 squared is 64 times x squared squared is x. So that gives me x to the 4th minus 64x is equal to 0. So x times x cubed minus 64 equals 0. So x is 0, or x cubed minus 64 is 0, which means x cubed is equal to 64, which means that x is equal to 4. So this is the point 4, 16. And we're revolving around the y-axis. So if I make slices along the x-axis, they're going to be parallel to the axis of rotation. So I'll be integrating with respect to x when I do my shells. So there's my representative shell. My radius is going to be equal to the distance from the axis of rotation to my shell, which is just x, and my height is going to be the top minus the bottom, which is the square root minus x squared. So volume would be equal to, x's go from 0 to 4, 2 pi times x times 8 times the square root of x minus x squared, which is 2 pi times the integral 0 to 4, 8x to the 3/2 power minus x cubed. And then 2 pi times 8x to the 5/2 over 5/2 minus x to the 4th over 4, evaluated from 0 to 4. I'm going to do some plugging and chugging. I got 384 over 5 times pi. Now I'm going to draw another picture and do it the other way. You try it and we'll compare answers. And again, it wasn't really hard. You just had to rewrite your functions with x's in them instead of, or with y's in them instead of x's, excuse me. So we have the square root of y, and we have y squared over 64 because we divided both sides by 8 and then squared both sides. We found our inside radius is the one that was originally the square root, so the inside radius is y squared over 64. The outside radius is the one that was originally the parabola, so x equals the square root of y. And then we did pi times outside squared minus inside squared, and we got the exact same thing. Now, the next one doesn't tell you to do it both ways because one way is easy and one way is hard. Determine the volume of the solid obtained by rotating y equals 3 sine of x between 0 and pi about the x-axis. Use the method of your choice. So, use the method of your choice. We'll come back and I'll show you the easy way and the hard way. Okay, here's the easy way. Since I was given my function with x's in it, I think, ooh, I'd really like to integrate with respect to x unless something weird's going on. So if I want to integrate with respect to x and I'm revolving about the x-axis, that means I want to use discs or washers. And in this case, it's just discs because I make slices that are perpendicular to the axis of rotation. And there's only one radius, which is 3 sine of x. So pi times the radius squared, because each of those slices is just a circle. So pi radius squared, so I should have pulled pi out. I pulled the 9 out, and then I had sine squared. I used my half angle formula. Now, if you wanted to do it with respect to y, it took me both sides of this. So what I had to do was to figure out how to graph the inverse sine function. So let's start with that. Because you know that if I just look at arc sine of y over 3, then that's only going to give me this piece right here. And I need the rest of it to get my whole thing because my height is going to be this minus this. So I had to figure out how to get that other side of 3 sine of x using inverse sine functions. And first I looked at the arc sine from -3 to 3, and I realized what I needed to do is shift it over pi units. So it's pi minus the negative minus arc sine of y over 3. So this is the right hand side of sine. This is the left hand side. Yeah, it's a lot harder. Leave it a sine. So I had this would be the right hand side of my height. This would be the left hand side of my height. And my radius is just equal to y. So I have the integral from 0 to 3, 2 pi y. There's my radius. And this is my height because it's the left-hand side minus the right-hand side of that sine curve. So then I simplified it a bit. I divided it into two pieces. This first little piece here was easy, and it gave me 9 pi halves. And then I have this piece. So I took this, and actually I started just by looking at this right here, the y inverse sine of y over 3. That took integration by parts. But then when I got into my integration by parts, I ended up with y squared over 2 times 1 over the square root of 9 minus y squared, which required trigonometric substitution. So I did the trig substitution with y equals 3 sine theta. I ended up with 9 halves of the inverse sine of y over 3, which was theta, sine of 2 theta over 2, which is 2 sine theta cosine theta. So I used my triangle and figured those out. And then I did 4y times that because that's what this whole piece is here, the star. And I plugged in from 0 to 3. And it took a lot of effort. I brought it over here and I ended up with 9 pi squared over 2, which is exactly what I got when I just did it using sine. And it took up this much space as opposed to that much space. So sometimes it's a whole lot easier to use one method, and I would never force you to use the harder method. Last practice problem. Use the method of your choice. Determine the volume of the solid obtained by rotating x squared plus 2 between 0 and 4 about the line x equals minus 1. Method of your choice. Meet you back here and we'll compare. Okay, once again, if I stick with the variables I'm given, I have y equals x squared. I'll make slices along the x-axis, which would be parallel to my axis of rotation. My radius is equal to the distance between the x coordinate and -1, so x minus -1 is x plus 1. My height is just the function, so x squared plus 2. So we go from x is 0 to x equals 4, 2 pi radius times height. If I go with my slices perpendicular to the axis of rotation, then I have to divide it into two pieces. I have this part here that's just a little donut because its inside radius is just 1, its outside radius is 5, so it has area 48 pi, volume 48 pi. But then from y equals 2 to y equals 18, we have the inside radius is the function, which is square root of y minus 2 minus -1, so plus 1. And then my outside radius is again 5, because all the way from 4 to -1. So I end up with 512 over 3 times pi. When I do all of that integrating, I end up with the same thing, but easy way. Not as hard as the last one, but still a little harder. So if you have to divide it into 2 pieces, why do that when you can use shells and just do it an easier way? It's all up to you. You have the power. You can do this.